Okay, I see that many of you have had problems with the part of data augmentation. It was taking a long time in Google Colab. I was asking if anybody has done it locally.
Switched to local and the problem was solved. It's a
Okay,
Colab
so
problem.
it's possible it has to do with the fact that in this data flow, when it generates the new samples, it has to do in and out of writing an image and getting, I don't know. So I don't know why this is having a problem. But essentially, you can run that part locally and there is no issue, no?
Yeah, locally no issue at all.
And what kind of accuracy did you achieve?
Sorry?
What accuracy did you get with the data augmentation? Did you see an improvement?
There's some kind of error. I don't know precisely what happens, but it just kind of reinitializes the weight instead of loading the already trained ones, so it's quite bad accuracy. I don't know
All
why
right.
this happens. Maybe
Okay.
someone else has better results?
I don't hear anybody. I also wonder if, like, where did you get to in this? It's a very short time. I think we finished 40 minutes ago. So, were you able? So, Roberto, you were able to get to the end, but other people, you want to tell me what issues you had or what you got? Otherwise, I will ask a question. For example, I'm going to ask. Not the many Pablos, I'll ask Neus. There is only one Neus.
Hi,
Hi Neus, can you tell us where you got to?
well, I didn't arrive to the end of the notebook because I didn't understand what is exactly the batch size and the training epochs. I have some doubts about that.
Yes, okay. So the data sets that you are putting through the network is very large. It's about 60,000 events, right, for the training. And to make things faster, instead of making the whole data set pass through the network, meaning you input in the input layer those numbers, and then they go through the different layers, then it gets to the output and so on. Instead of doing this with an X, with an input, that's the whole data set, usually what you do is to do batches out of it. So, for example, you have 60,000 events and you do 30 batches. So there will be 60,000 divided by 30 events that are run and passed to the network at once. Okay?
Okay.
So that's the meaning of the batch size. And the number of epochs is essentially the idea is that you are going to run through the network and many times so that you get a better approximation to what these weights should be. Essentially, you run it and try to get a good value for those weights. Starting from this point, you run it again and you get a little better value for the weights, and so the accuracy goes up, the the loss goes down, and that's what the epochs are. The epochs are reruns of the same story, but trying to improve from the epoch before. So what can happen is that you start running and you start improving accuracy, and at some point it doesn't improve anymore, so it gets to a plateau. Or worse, that it starts getting to a lower accuracy, so it's getting worse. That means that you should stop running, obviously, but also try to modify what you are doing. And when you do convolutional neural networks, you see that, let me just share my slides, maybe that's easier. Share application, no, this, here. Here, that's the output of what's happening during the CNN running. Epoch here starting, and this is the last epoch. Can you see my
Yeah.
Perfect. So at the beginning, the validation loss, the loss, when you run through your whole 60,000 events is a number, a value. Then in the next iteration, you start getting better, because the cost function is going down. And at the same time, then the accuracy is going up. Now, for each of these epochs, apart from the 60,000 training events, you also have reserved 5,000 that you are going to use as validation. So coming back to here, here. The idea is that as you are training, you also use this additional set of 5,000 events to see on the spot how much you are able to generalize. How, when you see in other events, you are doing well or not. And that's, that goes pretty fast, but that's what you see here at the beginning, the validation loss as the training loss are going down. Then, because it's a smaller data set, it's only 5,000 versus 60,000, you see how it fluctuates. And at some point, whereas the training is going down and getting better, so it looks like you are learning more, you see that the validation is not learning. The contrary is going up. Here, it means that you should not keep running. You should not keep trying to get better at describing the training data set. And here you see it as well, whereas the accuracy on the training data set is going up and it gets to very high values. When you actually contrast it with the validation, it's plateauing around 97%. And indeed, when we then check with the test data set, so a data set that we haven't seen neither here or there, we also get about 97%. So this means that your neural network is kind of trying to get better and more specialized at the characteristics of your training data set, but it's not really generalizing as it should. Okay, so what other things were confusing, Neus?
Yeah, I don't know. I don't.
But you got all the way to here, at least.
Yeah. That's. I didn't catch the definition of these terms, of these concepts.
That's fine. Yeah, that's fine. That's the point of this. And I'm sorry you didn't have time to go through this. One thing we can do is to, tomorrow, instead of going towards unsupervised, I can as well just spend more time explaining a bit more. It's true that I packed a lot of information in this session and it was a bit too much. So if you want by email, you can tell me whether you will prefer to have like a review session for this where I explain a bit more the context and the terms, because certainly I overdid it in terms of one session. But Neus, in principle, with more time, you will have had time to look at Keras, the definition of sequential. You will have had time to look at what dense is, what this is the number of neurons, what is the input shape, and so on. But probably you didn't have time, right?
Yeah.
Sorry.
No, totally understand. That's yeah, go ahead.
Can you hear me?
Yes.
I actually have a question about the dense because I didn't understand exactly what the 32 means. For what I understood, like I have an input of 700 and whatever pixels, and then the output is 32, but I didn't understand exactly what does this mean. So is the first layer that I have an input of 700 and something, and then in the second layer, the new input is only 32, or I misunderstood?
No, you understood correctly. So, sorry, I was googling it, so you see where the documentation is. I'm sure that you have a look at that. The idea is how many neurons you are going to have and what the input to those neurons should be. Okay, so why is 784? Is simply because we remember that for the fully connected neural networks, we can have unzipped the 28 times 28 bins under gray levels. And that means that we did an array of 784 inputs, where the inputs are the levels of gray. So in the first layer, you have to define, it's going to be a set of neurons whose input, what they are going to process, you need to give the input of your inputs. In this case, it's an array of 784 inputs. Whereas, let me go down for the CNN. When we reshape it, and we use the images for the convolutional 2D, what you get is this 28 times 28. So that's the input sheet. So when you build your architecture, let me just go back to this. You just need to make sure that whatever you put in the middle, in the hidden layers, you can do lots of things. You can add all kinds of layers, but the input and the output have to match your inputs and your outputs. In this case, the first layer needs to have as input shape wherever you are inputting the images in terms of arrays, and the output layer needs to have the shape of your outputs, which is, in this case, is again a set of neurons made of the number of classes, so the 10 classes. Okay?
Okay, I understand. So the reason why, for example, in the second layer, I don't have to put the input shape is because it's 32 is the output of the first one, right?
Exactly.
Okay.
And this is going to be what is going to be inputted to the next one as well.
Okay.
And here you could have done, when you have time, add stuff like dropout. Adding dropout meaning that in the, let's see if I have let me show you a plot. Dropout. Let's just plot something like this, right? This is a neural net, and let's see that these are inputs on the bottom and the output is in the top. And what we are seeing here is that, for example, when we train with a fully connected neural network, if you just looked at the training, it will look as if you are learning quite well, it's going down quite smoothly, and if you had trained more than 20 epochs, you will have even improved, right? Here the same, if you just look at the blue line, which is just the training, you will think that we are continuously going to higher accuracy, so there's no point of stopping, we should have gone even higher. And that's the value of having the validation set apart to give us a test of whether we are just fooling ourselves in quotation marks. Here, clearly, we think we are doing well, but this training is not generalizing. It's not working well on the validation, so it's not going to work well in any other new situation. Well, meaning it's not going to get better than 97%. That's what I mean. This is a signal that we are overfitting. It's a signal that this network is fixing or is trying to explain features in the training set that are not generic, that are just of the training set. So there are many ways to
Veronica, one
avoid.
question.
Yeah.
So how exactly do you define this loss? So what, like mathematically, I understand it's a measure of how good you're doing or how bad you're doing, but how do you define it?
The loss is here. Let me just count. The loss is the cost function, which in the case of the classification problem we have is called categorical cost entropy. Okay, it's a
Right.
function which, if it was for, let's say, in linear regression or any other problem, it would be simply the error, the
Okay.
root. Okay, so in this case, it's something.
It's
more
this
complex.
entropy, this logarithmic entropy that you showed in the slides.
Exactly. With a minus sign, so it's something that you are trying to minimize, not maximize.
Okay. Yeah, it just has some weird value, but
See, it's not like if your loss is your RMSE, your square error, then you know what it means. But when it comes to here, it's this log likelihood with a minus sign.
right. I just wasn't expecting this 0.1 kind of value. Okay, yes. This is normalized, I guess, or something.
As to the weights and the biases that are being used. Yeah.
Okay.
What you care about is whether it's going down. The absolute value is not that important. But so what I was saying, yeah, and what I was saying is this thing about overfitting. This neural network is overfitting. It's looking at trying to explain features that are in the training. So it's getting better at describing the training set. It's fitting very well, but it's not predicting very well. Okay. So there are many ways to avoid this. One of them is what we discussed yesterday, is to use regularization, where you make sure that if the reason why here we are overfitting is that some features are out there, they are like outliers, the regularization will take care of them. But another way also of making sure that you are not fixating too much on features that are not there is using dropout. And the idea is that in dropout, in a random fashion, you are going to switch off a portion of your neurons. So as you are running your events back and forth in these neural nets, from time to time, you are going to set by hand and in a random fashion a proportion of that. So to do that, you will just simply add in when you build your neural network, let me go back to where it is, here, you could add, for example, comma dropout equals 0.2, which means from time to time, and in completely random fashion, switch off 20% of my neurons. What it does is that as it is training and is getting better and better and better, as I was telling you, sometimes what is going to happen is that at some point it realizes that some inputs are not that important, not that relevant, and hence it's not going to activate them in the next round. But what if that decision is wrong? What if that decision is actually informed by features in the training set that are not real or not generalized? Then to avoid that is where you use dropout. So you are at a certain level of randomness to prevent the network from overfitting. And there are other things one can do, but these are the most common ones. Regularization to avoid outliers taking over, and dropout to avoid patterns that are fictitious to actually take over as well. Any more questions or comments?
Sorry.
Please, Veronica.
Yeah, the first
May I
person
ask
that
first?
sorry, somebody was talking before you. Could you speak up, please?
Yes, it was me.
Yeah.
So about the regularization in this case, what should we use? I mean, the one that we saw the other time was for a linear regularization, for the linear regression, right? With alpha equals 0. In this
Yes.
case, we should use some other values of alpha.
No, you could. Well, again, it's you who decides how you are going to regularize. So you could use L1 or L2, and you could use them with a particular value of alpha. And then you might be thinking, and so what do I do? There is no recipe. Well, the recipe you want is you start with regularization, especially when you see that there is some form of overfitting. The regularization is added in the definition here. Sorry, no, over here. When you compile the model, you can add the regularization with a fixed learning rate parameter. And what you're going to see is that, let's go back here. When you add regularization and is effective, the regularization is going to change the rate at which this is learning. So instead of being so steeply going down, it's going to take a bit longer, but it might then be able to generalize better. What is going to happen as well is that you are a regularization there, and wherever you want, with a given learning rate. You might see that you need to run further in order to achieve the full learning. So again, it's something that I'll allow you to play with as part of your, let's say, homework with this notebook, is to add regularization, add dropout, and see the effect. Here you have a good example to use it. This is not good. It's good, but it means that if we had insisted on training for longer, we would have achieved for the training about 100% accuracy, and actually this would have been only 97% accurate in reality. So this is a good example to start using dropouts and regularization.
Okay,
And sorry, the person that was talking afterwards, do you mind talking now?
Hello? Can you hear me?
Go ahead. Yes.
Okay. As you said when we was looking at the slides, that's a supervised machine learning problem because we already know the different levels. So we can make the difference between them.
Yeah.
So my idea is, can we add some layer if we already know some difference between levels? Like add a human vision to call it in a way.
Can you ask this question again? Sorry, it's because the sound
Sorry,
was breaking up. It's me. It's my side that is breaking up.
Okay, imagine that we know any difference between levels because, I don't know, that's a very easy example because we're talking about numbers. But if we were doing, I don't know what, but we know the difference between levels, may we add some layer to make the computer distinguish between them?
I see. So let's see if I understood this time. So you're saying now we have images and the labels. So we know what
Yeah.
the labels are, and we know what they correspond to in their images. But imagine that we had just images. Is that right? Are you asking?
Yeah.
Just images, and then by eye you see that you as a human, you know that there are zeros, there are sevens, there are eights, and so on. So will the computer be able to, just with the images, tell you that there are 10 categories among those? Is that the question?
Yeah, but for example, imagine that we have to distinguish between the sky and a felt. So human can solve it, like for example, with the color. May we add it to the? Is there a manner to script something to like make the machine do it itself?
Sorry, I didn't want to interrupt, but you say, imagine that we had, and say two words where I could not understand them. Again, because the sound is a bit crap, I'm sorry.
Sorry, maybe my microphone. So
No, it's probably me. Yeah.
if we know difference between levels, can we add to our code, or that's not how it works?
If we know the difference between the labels, what you mean that if we know that there are 10 labels that we should assign, or
For example,
so in principle, what I was going to tell you tomorrow about is this unsupervised machine learning, right? Where this is the problem we are setting up. You have images, you know that they cluster into 10 clusters. Will an unsupervised method be able to do that? And yes, you could inform your clustering algorithm by telling it that you expect 10 labels, or that it should obtain 10 labels. So yeah, you could do that.
okay, thank you.
You're welcome. I'm sorry for the sound problems.
No worries.
Okay. Any more questions? I mean, I'm happy to spend the lecture tomorrow just going over this in more detail or going over your questions, because I know this is a lot to ask in just no time, right? So let me know, and if so, we can spend the lecture tomorrow doing that, and just move the one-off and supervision to Thursday, and it's absolutely no problem. Just let me know by email, or okay?
Sorry, I have a question.
Yeah.
In the convolutional neural networks, the last layer is a dense layer with 10 nodes. What's that mean?
Yeah,
You have a node for each possible output, and if it's so, that means that we give a probability to each output, a possible output.
Yeah, that's it. No, you got it. So in the CNN, you see at the beginning we input the images, it does stuff, but the final layer has to give an output that is of the form of our outputs, which is the probability of staying in any of the 10 categories. Okay, so the output in here is going to be for category 1, which is the number 0, probability 10 to the minus 7. For category 2, the number is the probability of whatever, and so on. And the highest probability will be the number that is assigned to that image. But
Okay,
it's not. Go ahead.
Each of these probabilities are binary probabilities.
Being as probabilities. Sorry, I didn't. Again, it broke.
Each of these probabilities are defined like binary probabilities. I mean, 0 means this level is not assigned, and 1 is assigned, or is something more complicated?
Look, it's
I don't
here.
know.
You want? See, no, don't worry. It's perfect. So now it's not a binary problem, right? It's not like in the cats and dogs, where you give me an image of a cat, and if I'm a good algorithm, I will tell you this is a cat with 19% probability and a 2% probability that is a dog. Here we have 10 categories. So the output of showing an image will be this image. It has that probability of being a 0. Can you see my pointer, by the way?
Yes.
Perfect. That of being a 1, 2, 3, 4, 5, 6, 7, 8, and 9. So obviously this guy happens to be an 8. No, yes, sorry, an 8. It has 0.9999 probability of being an 8. Okay?
Okay, I got it.
Perfect. More questions? If not, again, I mean, I'm packing a lot in this course, and there is absolutely no problem to slow down a bit. I understand this has been a big call, and for me, it's important that you understand today's lecture and the notebook, because with just this notebook, you are going to be able to do lots of stuff. So there's really no point on rushing through the next unless you really understand what's going on. So just send me by email or Slack or whatever you prefer to have a continuation of this lecture tomorrow, and we'll just do supervise on Thursday. Absolutely no problem. It's the first time I give this course, and it's normal that I'm overdoing it a bit. I tend to be a bit tough. Okay. All right. So I guess everybody should go on it, no? All right. Talk to you tomorrow then. Send me your comments by Skype.
Okay.
Bye.